4, which is on what's called synthetic division. Just so I don't forget, the book names this after the person that I think figured it out, and it's called Horner's algorithm. So if you see anything in the book that says use Horner's algorithm to divide, it just means use synthetic division. Okay? That's what I call it. So I told you that there are some problems that we can factor because the answers come out nice, and there are other ones that would be very difficult or impossible to factor because the answers don't come out nice. In general, if a problem has what's called a rational root, we can find it. Okay, remember what rational means. It means you can write it as a fraction. If a problem only has irrational roots, then we're out of luck. All right? There's no trick that I know of to find the answers. If it's a quadratic, sure, quadratic formula will work fine. But I'm talking about what if it's higher than quadratic? What if it's like a cubic or a quartic? Well, in order to be able to factor a problem that's a higher degree like that, we have to be able to find an answer that's a root, that's a fraction. Okay? And I'm going to show you how you can always find answers that are fractions. There's a way to do it. It's called the rational root theorem. So in the rational root theorem, you're going to have a polynomial, okay, something like that. When we do a problem, it's going to look more like that. You'll have your highest exponent term, and it'll go all the way down to the constant. It doesn't have to have every term like long division. The cube term is missing, the fourth degree term is missing. That's fine. But you're going to have a polynomial. And the only thing that's going to be important in this polynomial is really going to be that number there and that number there. Those are the only two things that are going to matter. The coefficient of the highest degree term and the constant. And if you know those two numbers, you can figure out if your graph crosses the x-axis at a fraction. It is important that the constant is not a 0. If it was a 0, this method's not going to work. I thought there was one other thing. I'm not worried about all this. Okay, that's fine. Yeah, so we just have to make sure that the constant is not a 0. If it is, that's a little different. We're not gonna look at that. I mean, it's very possible you have a polynomial with a constant of 0. It's just this theorem will not work. So you'll see why in a second. So if there is a rational root, meaning it crosses the x-axis at a fraction, it's going to look something like this. Okay, that's a fraction. The fraction is going to have a numerator and a denominator. Okay, I'm going to call the numerator of the answer P, and I'm going to call the denominator of the answer Q. P, which is the numerator, has to be a factor of the constant. So that's the number that's at the end. P is always a factor of the constant, and Q is a factor of the leading coefficient. So what this theorem does is technically it doesn't give you an exact answer. This theorem gives you a list of possibilities. You have to still check, but at least you have something to now check. Okay? So that's what this theorem does. It gives you a list of options. Not every possible option that this theorem generates is a root. Okay? To figure out which of the options generated by this theorem are actually zeros, that's where the graphing calculator is going to help us. But this theorem at least narrows down the options. Because if I just give you a random polynomial and ask you, where does this cross the x-axis? I'm gonna go right back. You don't know where to even start. Like where do you even look for zeros for this? Are they in the thousands? Are they in the millions? Are they in like 0.2? Like where do you even look? This theorem is going to basically tell you where to look. So we're gonna do an example, and I'll show you how the theorem works. The thing to remember is P and Q are factors. P is a factor of the constant. Q are all the factors of the leading coefficient. So remember, factors of 6 are numbers like 1, 2, 3, 6. And -1, -2, -3, -6. Those are also factors. All right, let's try this. Does everybody have the top part? Okay. So I want to list all, and I'm just going to put in the word here, possible, because this theorem gives you a list of possibilities. So list all possible rational zeros. So the first thing you want to do is identify all the possibilities for P and all the possibilities for Q. P are all the numbers that could be in the top of the fraction. Q are all the numbers in the bottom. P are the factors of the constant. I kind of just said this, but what are the factors of 6? Yeah? Right. So plus or minus 1, 2, 3, and 6. So if this graph crosses the x-axis at a place that's a fraction, if the numerator will be one of those 8 numbers. Guaranteed. Okay, the denominator are all the factors of the leading coefficient. What are all the factors of the leading coefficient? Yeah.
Plus or minus 1, 2, 5, and 10.
Plus or minus 1, 2, 5, and 10. So if this graph crosses the x-axis at a place that's a fraction, the denominator for that fraction will be one of those 8 numbers. Now we have to list
1, 2, 3, and 6.
Those are all the factors of the number 6. All the numbers that divide into 6. And then all the numbers that divide into 10.
How do you know which ones are P and Q?
P is the constant at the end, and Q is the leading coefficient.
Okay.
So P is the factors of the constant, Q, leading coefficient. Now we have to write all the possible P over Q. So now we have lots of options to write down. So this is going to be a list of possible rational roots. Okay, so the way I would do it, you have to just try to do it systematically. Let's start with P being a 1. Okay, so P could be a 1. And then we could do 1 over every Q value. So we could have 1 over 1. We could have 1 over 2. We could have 1 over 5. And 1 over 10. And the negatives. So those are all the possible rational roots with a 1 in the top. Now let's do all the possible rational roots with a 2 in the top. What would be the first one? 2 over
1.
Yep, so we're going to do 2 over 1. Which you could just write 2. But yeah, 2 over 1. What's the next one you would do? 2 over 2, but we already have that one, so that's a repeat. The next one would be 2 over 5. And the next one would be 2 over 10, but
1/5.
We already have that one, so that one's also a repeat. Okay. What's the next value we would do in the numerator? 3. And what's the first one we would do with a numerator of 3?
1.
3 over 1. Next one?
3 over 2.
3 over 2. We don't have that one. The next one?
3/5.
3/5. And 3/10. We don't have any of those. And the last one, that's with a denominator of a numerator of 6. Okay, so what would be my options for a numerator of 6?
6 over 1.
6 over 1. Okay, the next one?
6 over 5.
What about 6 over 2?
That's 3 over 1.
That's 3 over 1. So we already have that one. What's the next one?
6 over 5.
6 over 5. And the last one would be
What would be 3 over 5?
the last one would be 6 over 10, but we already have that one is 3 over 5. Okay. Any questions on how we generated that list? And those numbers are not spread that far apart. The biggest one is 6, the smallest one is -6. So now I know if I'm looking at my graphing calculator, if I look between 6 and -6, that's where this graph has to cross the x-axis if it crosses at a fraction.
Like, we're probably not going to be getting this on the homework, but like on a test that has this problem generally, is there some other way to do the plus or minus thing? Like, you have to say plus or minus all of those, or can you just say like plus or minus and then colon in that, like, answer-wise, what's like the easiest?
I guess you could do it that way.
Okay.
Yeah. I usually just put it on each one because we generally don't have this many possibilities. This is a lot. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 24 different possible places it could cross the x-axis. That's a fraction. It's not even a guarantee that it does cross the x-axis at any of those numbers. But if it's going to cross at a place that's a fraction, it has to be one of those numbers. It has to be.
Can you explain to me how you got your P, like the 4?
The P?
Yeah.
P is all the factors of the number 6.
Oh.
1, 2, 3, and 6. Q is all the factors of 10. 1, 2, 5, 10. A lot of times you have a number here that's like a 3 at the end, so now that's nice because the only factors of 3 are 1 and 3. So it's a lot less options. Because this had a lot. Any other questions on how we generated that list? Okay, so now, that's the same problem we just did. I want to show that that graph has one real root, not imaginary, and I want to show that it is irrational. Okay, I want to show that it's irrational. So the first thing we'll do is let's bring it up on the calculator and type that in. So you've got 10 x to the 5th minus 3x squared. Make sure you get out of the exponent. Minus 3x squared plus x minus 6. Okay, I'll do zoom 6. And let's see what it looks like. How many times does it cross the x-axis? Yeah, it crosses once. And what I want to do is take that and make that picture a little bigger so we can see it. Maybe. Oh, okay. So there's our picture. And what I want to do, once I make it bigger, is look at it and compare that to the list of possibilities on the other page. Are there any options in this list that look like it could be close to where it crosses? So this is narrowing down the list now. Some of these They don't even look close, like positive or negative 6. No, that's way over there. So I'm looking in that list. Is there any that you think look reasonable? Yeah? I would say positive 1 looks like it could be an answer. Is there any number in that list that looks like it could be close to that? Yeah? I would say positive 6/5. It's 6/5. That's just over 1. That could be just over 1. We don't know. We might have to zoom in a little bit. Sorry, just positive 6/5. I don't really think there's anything else that's even close. Like 1/10 or 2/5, that's 0.4. None of those other numbers look close. So if I ask you to take your list of possible rational roots and narrow it down, I want you to graph it and see if any of these possibilities look close to that. Okay? So that's narrowing down the list. Now let's find it. To find it, we use the calculator. We'll do second calc, 0. Pick a point left. Pick a point right. Hit enter. Okay, and then what we get is 0.9505. Let me make that bigger so you can see it. It says the root is 0.9505. How do you know that 0.9505 is irrational? Why does 0.9505 have to be irrational? Yeah.
Because it's not one of the options. All the options are rational answers.
Not one of the. No, it's not one of the rational options. These are the rational options for this problem. There are no other ones. The real answer is 0.9505. Are any of these fractions 0.9505? No. Since the number you got is not in the list of possible rational answers, then it has to be irrational. Okay, so how would you write that? So we could say the root is about 0.9505, and that number is not in the list of rational options. So it must be irrational. So this is the least satisfying kind of rational root problem because we listed all the roots, we graphed it, and this graph doesn't even cross the x-axis at a rational root. Okay? The theorem doesn't guarantee that any of these are the answer. It just says if it does cross at a fraction, then one of them will be the answer. But that's only if it crosses at a fraction. This one didn't. So how would you find this without the calculator? You'd be kind of stuck. It's a 5th degree polynomial. We definitely don't have any kind of formula for that. It'll be a really hard problem to figure out without the calculator. I'm not sure how to do it. Yeah.
So the equation that we plug into the calculator to figure it out, y equals is going to be 0, so potentially couldn't you figure out what x is, like, with all those things based off, like, what the 0 intersect is? Because, like, yes, there's, like, multiple x's, but it's got to be, like, some way, like, mathematically with a formula that you can just do on paper.
Yeah, there has to be some way to probably do it, but I have no idea how. So there must be some way, but it being a 5th degree polynomial, I don't see any tricks. I mean, I don't think factor by grouping is going to work. I just don't see any method that I know to do it.
What's the, like, highest degree you could, like, factor out on, that you can factor out by paper? Because I know, like, y equals ln plus b, you just need to know what the what the slope is, what the y-intercept is, and what the y you want is. And so, like, you just do that, but, like, what's the highest degree that you could, like, go to? Because x squared, like, should be simple enough.
I mean, if the numbers work out nice, there's no limit. I mean, you could factor something with an exponent of 100.
Oh, yeah.
As long as the answers were nice. Like if you had a difference of 2 squares, like you could factor x to the 25th minus 36 as x to the 5th minus 6, x to the 5th plus 6. I don't know if you consider that kind of a cheap one, but it has a power of 25 and I just factored it.
Yeah.
So if it's a special case, then there's no limit.
Yeah.
You can go really high. But if it's just generic, I mean,
You can't.
quadratic is, we can definitely do, but the problem is if you don't get rational answers, you're going to have messy factors. You might have like x plus root 3 over, root 3 over 8 and then x minus root 3 over 8. You're going to, you might get some fractions in there. So you'd have to use quadratic formula to figure out how to factor it.
Okay.
And generally, we only factor it when numbers are nice. We don't really ever write down factors like x plus 3 root 2 over 6 and x minus 3 root 2 over 6. Those might have been answers you got from like quadratic formula. And we generally don't factor like that. But you can if you know the quadratic formula.
Final thing, if we plug the 0.95 thing into that equation, it should come out to like really close to 0.
It won't, it's not should, it will. I guarantee. Yeah.
Well, it's just because it has like a lot of like small decimal points after it that we like can't be like hyper exact on it.
Oh, well, yeah, because of rounding, it won't come out exact. But
Yeah.
0.9505 is essentially the root. Yeah.
Thank you.
Yeah. So, whenever you're dividing by x minus c, okay, that's the case where we can usually use rational, what was it called yesterday? Remainder theorem. We can also use something called synthetic division. So, synthetic division is a quick way to do division as long as you're dividing by something that's x minus a number. So what I'll do is I'll give you the steps and we'll do the division, kind of the problem at the same time. Now, when we do this one, it says to show that 3/2 is a root or a 0. If 3/2 is a root, what does that mean would be a factor? Like what would you plug 3/2 into so you get 0? Yeah. So your factor, it's going to have a variable in it.
Oh, would it be x minus 3/2?
Right, it would be x minus 3/2. So in order to show that 3/2 is a root, I'm really going to show that this is a factor. That's the same thing. We talked about equivalent statements between roots and factors yesterday. And to show that something is a factor, all I have to do is do division and get a remainder of what? 0. That's what I'm really going to do. I'm going to divide this factor into that polynomial and show you that the remainder is 0, which proves this is a factor, which also proves this is a root, which proves it's an x-intercept, which proves it's a 0. All the same thing. So how do we do that without using long division? Well, first thing we're going to do is you put down the number after the minus sign, which is the 0, or the root you're trying to work with. And then you put like a bracket around it. Backwards L. And then you're going to put down all the coefficients of your numerator. Fill zeros in for anything you're missing. Are we missing anything here? No. So we have 2, -5, 1, 3. Draw a line like that. Now, once you do that, this entire problem is going to fit in this space. That's another nice thing about synthetic division. It can fit in a smaller space than long division. Okay, bring down the first number. 2. The next thing we're going to do is we're going to multiply the number on the outside by the number we just brought down, and we're going to put that answer in the second column. What's 3/2 times 2?
That's 3.
3. So you multiply those two numbers and put the answer in the second column. Now add those numbers up. What's negative 5 plus 3? Yep, negative 2. And now we keep repeating that until we're done. And then when we're done, I'll tell you how you interpret your answer. Okay, so now do it again. What's negative 2 times 3 halves?
Negative 3.
Negative 3. And now add that column. That's not what I wrote. It's negative 3. Okay, add that column up. What's 1 plus negative 3? Negative 2. And now we'll do it one more time. Zach, what's negative 2 times 3 halves?
3. Negative 3, sorry.
Negative 3. Yep. And Ryan, what's 3 plus negative 3?
0.
0. And you're done. Anyone have a guess what that number is? That's your remainder. And how about this part? That's your quotient.
Squares minus 2x.
Stop responding, that's what happened.
Yeah, thanks. Yeah, so that last row is your quotient and remainder. A lot faster than long division, but it only works on this kind of denominator. So this is your remainder, and this is your quotient.
Wait, so how do you determine if you can use synthetic division, or if you have to do it out and you see like, oh, I can't do it?
Synthetic division will always work as long as your denominator is x minus a number. That's when you use synthetic division.
Oh, okay.
It has to be x minus.
Can you just do it just the problem all again? So I was writing down how to do it, so I just got lost.
Yeah, we're gonna do a couple more synthetic. I think I have another to show you, but I can't right now. But yeah, we do have one. Yeah. So the quotient, just go down a little bit. This is the constant, linear, quadratic. So if you're gonna write your quotient out, it's 2x squared minus 2x minus 2. Remainder, 0. So because the remainder is 0, what does that mean about x minus 3 halves?
Factor.
That's a factor. What does that mean about 3 halves?
Is that word like?
It's a root. 3 halves is a root. So now, if you were going to try to factor this 2x cubed minus 5x squared, x minus 3 halves is one of the factors. And what's the other factor? We know it from the work we did, yeah? The quotient. It's 2x squared minus 2x minus 2. If you multiplied that out with FOIL, you'd get back the original problem. So that's how you can factor a higher degree polynomial. But the thing is, I gave you this 3 halves. How would you have figured out that this number could have been a root if I didn't give you 3 halves to start with? Well, you might not know where to look on the graph. So, because it could be in the millions, it could be in the thousands. You wouldn't even know where to start. What tells you where to look? Basically, it gives you options to look at. Yeah? Yeah, the rational root theorem. That's how you would have gotten 3 over 2. It would have been one of the rational roots, factors of 3 divided by factors of 2, and then you could have narrowed it down and looked at the graph. Yeah. Okay, so let's do synthetic division again. We're going to find the quotient and the remainder when we divide by x plus 3. Now, does that fit exactly the pattern I said it should? Not quite, but can we modify it so it does have the right pattern? Yeah?
You make it like 3 over 1. Right? Actually, no, that's not okay.
Cool.
X minus negative 3.
Right. It's got to be x minus a number, And whatever the number is that's after the minus sign, that's what goes on the outside. So in this problem, I'm dividing by x minus minus 3. So put a minus 3 on the outside. What are my coefficients going to be?
3, 7, 1. Oh wait.
3, 7, 0, 1, negative 11. So you got to fill in that 0 for the x squared.
Oh, okay, that's right.
Okay, bring down the first term. What's negative 3 times 3?
That's negative 9.
Negative 9. What's 7 plus negative 9? Negative 2. Now what's negative 3 times negative 2? Plus 0? 6 times negative 3?
Negative 18.
Negative 18. Negative 18 plus 1?
Negative 7.
17. Now negative 17 times negative 3?
51.
51. Plus negative 11? 40. So, is x plus 3 a factor of the original polynomial? No, why not? Because what?
Because you have a remainder.
Yeah, I have a remainder. I got a remainder of 40. It didn't go in evenly. So now if they ask to write the quotient and remainder, don't just leave it like that. That doesn't really tell me you know the quotient and remainder. Okay, remainder is 40. What would the quotient be? Kind of have to start at the negative 17 and see how many powers you need. Yep. Yeah.
Oh, my bad. 3x cubed
3x cubed.
minus 2x cubed
Yep.
plus 6x minus 17.
So there's your quotient and your remainder. SD. I should have said what that stood for. It's synthetic division. I didn't say that. SD is synthetic division. RRT is rational root theorem. Just quicker to abbreviate with those 3 letters. GC, graphing calculator. Because I think I use those terms in the next slide or so. Okay, show that 3 is not a 0. And I'm going to add using synthetic division. Because really, if you just wanted to show 3 is not a root, all you have to do is plug 3 in and show that we don't get 0. But the point of it is to do it with synthetic division. So if we're dealing with 3, we're going to show 3 is not a root. What am I going to show is not a factor? Yep.
X minus 9.
So what would be here that you would plug this number in and it would come out to 0? Yep.
You want the x minus 3.
Yes. So we're going to show that 3 is not a 0, which means we're going to show x minus 3 is not a factor. How do you show something is not a factor of something? Yeah.
You do the synthetic division thing.
And what's going to happen if it's not a factor?
If it's not a factor, it's going to have a remainder.
It's going to have a remainder. Yep. So we're going to divide x minus 3 into the original polynomial and show that we get a remainder. And once you get pretty good with the synthetic division, you can really do this pretty fast. So in this case, make sure you get the right coefficients. Bring down the 2. 3 times 2 is 6. 5 plus 6 is 11. 3 times 11 is 33. Minus 2 is 31. Times 3 is 93. Minus 3 is 90. And that's the whole division problem. So what's my remainder there? 90. So I just showed that x minus 3 is not a factor, which means 3 is 3 is what? 3 is not a 0. X minus 3 was not a factor. 3 is not a 0. 3 is not a root. 3 is not an x-intercept. That's how you show it. But up until this point, I've kind of been giving you the number to try, like 3. Or, in this case we did -3. In this case we did 3 over 2. Well, now you're going to have to use the rational root theorem with your graphing calculator before you get to the synthetic division step. So you're going to have to figure out the possible root on your own. So this one says find all rational zeros. The first step is to make a list. I mean, you can kind of look at that and have an idea, but really, when you have a problem with bigger numbers, you don't know where the roots are. Maybe they're in the millions. Maybe they're in the, who knows. So we kind of got to narrow down where they could be. And that's what rational root theorem does. All right, so let's do possible rational roots. First thing we need to do is the p's and the q's. What are my possible values for p in this case? Yeah.
Positive and negative 1, 2.
Yeah, not that many options. There's positive or negative 1 and 2. And what about my possibilities for q? Yep.
Just plus or minus 1.
Just plus or minus 1. So now I want to write down all the options. Like last time we had 24 when we did this. We don't have that many. What are the possible rational roots here? Yep.
Just plus or minus 1.
Just plus, yeah, that's it. So if this graph is going to cross the x-axis at a fraction, it's going to be between -2 and 2. So if I do a standard window, will that cover what I need to see? Yeah, that's fine. So let's put in x cubed minus 3x minus 2 and do zoom 6. Which one of these answers seems reasonable? There's, I think, a couple that could be it. Yep.
-1 and +2.
I'd say -1 and +2 both seem reasonable. So you can try either one. The way you could try it quickly is press trace, press 2, and hit enter. If y comes out to 0, well then you know it's a root. Yeah. So what we're going to do now is once you know that a number is a root, just like we did in this problem, once you know that this number is a root, you're going to divide through by it synthetically, and you're going to turn your cubic into a quadratic. And once you turn something into a quadratic, you can always solve it with quadratic formula. It's just you've got to take the exponent from a 3 down to a 2. And that's what synthetic division does. All right, so we think 2 is a root. Let's try. Let's put 2 on the outside. And then what would my coefficients on the inside be? Nope, this one. 0. And then -3, -2. Yep. Now, if this is a root, what are we hoping for a remainder of?
0.
Hoping for 0. So bring down the 1. 2 times 1. Add that up. 2 times 2.
-1. +1.
Positive 1. And then 2 times 1.
2. Remains 0.
Perfect. So now we can start making a list. 2 is a root. Now, find the roots of your quotient. Those are the other roots. So you took it from being a cubic, and now you have a quadratic. X squared plus 2x plus 1. That, I don't even need to use quadratic formula because it's factorable. How does x squared plus 2x plus 1 factor? Yep.
X plus 1.
X plus plus 1, x plus 1. That's a repeated root, which should make a little bit of sense looking at the graph. Remember I told you yesterday, a repeated root, the graph kind of comes up to it, bounces off the axis, and goes back down. We just have to know where it is. You can see it on the graph, and you can also see it here. What value would you plug into either one of these to make them 0?
-1.
-1. So the roots in this problem are 2 and -1. You don't have to write -1 twice. You're just making a list of roots. Each number is listed one time. But if you want to be technical, -1 is what we call a repeated root.
So P and Q, okay. So that's adding, how did you get the numbers at number 2 there? Where it says like 2 with a box around it.
Under the roots, two?
No, the one beneath it.
the 2? Well, the 2 was from this list of possibilities. We looked at the graphing calculator, and we said, okay, 2 looks like it's a rational root. So whenever you find a rational root, you divide through by it synthetically. And every time you divide, it's going to take this exponent down a number. Eventually, you have to get it to a quadratic. So if it starts out at like a 5th degree polynomial, you're going to have to find a rational root at least once to bring it down to a 4th. And if you can't factor that somehow, it doesn't work out nice, you're going to have to find 2 more rational roots to bring it down to a cubic and then a quadratic. So you'd have to do synthetic division 3 times, potentially, if that number was a 5.
Okay. So all those numbers where it says like 1, 2, 1, 0, that was found with the possibilities from the roots.
No, that's from the synthetic division process.
Okay.
Multiply, bring down, multiply, add, multiply, add, multiply, and add. So that's synthetic division. Multiply and add each time.
Okay.
You don't subtract. Some people mix that up with long division. Long division, you do subtract. Synthetic division, you don't. Okay, let's try this one. Find all rational zeros. I'm just seeing where we're at. Yeah, we don't do that. We don't do that. We don't do that. So we're like 2 slides. Okay. What's your first step to find rational zeros? You got to figure out your what's and your what's.
P's and Q's.
P's and Q's, yeah. Let's get the P's, Q's. What are the possible values for P here? This is going to be really nice.
Plus or minus.
Just plus or minus 1. Now, possible values for Q, not quite as nice.
1, 6, 2, and 3.
Yeah, we did 6 before. And what would be the possible rational roots when you write these as a fraction? Yep.
Plus or minus 1, 2. Oh, 1/2.
1/2, yep.
1 3. 6.
Okay, so I know exactly where to look for rational roots between -1 and 1. I just looked quickly at the biggest and smallest number in that list. So will a standard window cover what I need to see?
You could zoom it in more.
We could zoom it in more. We don't even need to do -10 to 10. It's never going to cross at those numbers.
So where did you get 1, 2, 3, and 6 from?
Those are the factors of Q, the leading coefficient. They're the factors of 6.
Oh, okay.
The only thing that matters in this problem really are those 2 numbers. Anything in the middle, if you change those -5s and 3s, it doesn't have any effect on the problem. At least, I will say it doesn't have any effect on this list.
Yeah.
It would affect the problem, but not that list. Okay, so 6x cubed minus 5x squared plus 3x minus 1. And now we're going to use the calculator to narrow down this list. I could have zoomed in, but I think you'll be able to tell. Well, maybe you can't actually. Zooming in would have been probably a decent idea.
I used the second trace
Yeah, where does it look like it crosses?
Right at the half.
I'd say it looks like a half. If you want to check real quick, just do what
It
Jacob just
crosses there.
Yeah. So 1/2 is a root. And it's the only root. So really we can stop at this point. If they wanted all real answers, you'd have to take the 1/2 now, divide through by it. And when you do that, the cubic would turn into a quadratic, and then you'd have to use quadratic formula to solve for the other two roots. But I can tell just by the way this looks, the other two roots are imaginary. If they were real, the graph would have curved back down and gone back up again, and it doesn't do that. So we've answered the question, we don't need synthetic division. In the next problem, it does say find all real, so you're going to have to use synthetic division. Okay, so find all rational roots. One half. Every polynomial always has as many answers as the highest degree. So a cubic always has 3 answers. I'm not writing all 3 because it didn't ask for the imaginary ones. So there's 1 real, bless you, and 2 imaginary. Tomorrow we'll do the imaginaries. So tomorrow is basically what we did today, just actually doing the imaginaries. Okay, so the last one says find all real roots. So real means all of them, the ones you can write as fractions and the ones you can't. Now it's a cubic. Do we have a formula that we know for solving a cubic? Yep.
The PQ one.
Well, I mean, like, do you have a direct formula?
Not
a theorem.
Well, a squared plus bx plus c is only maybe quadratic if you simplify it, or maybe if you use like 0 or something.
Okay, but that's not quadratic. That's cubic.
I guess we don't.
We don't. We don't have a formula for solving a cubic. Nobody knows the formula right now. I don't know the formula. There is one. I don't know. So quadratic is what we got to turn this into. Only way we're going to be able to turn this into a quadratic is if we can find what?
0.
What kind of 0?
A real?
No, not a real 0.
No.
More specific. A what? A rational 0. That's the only way we're going to be able to turn this into a quadratic. We need to find a rational root. So let's see if we can find a rational root. Okay, possibilities for P. Yep.
Positive, negative, negative 2.
Possibilities for Q.
There's 1 and 3.
Plus or minus 1 and 3. Possibilities for the rational roots.
Well, can we do 1, then
Okay, plus or minus 1.
and 2, and then 2 3?
I would do all the ones that start with 1 in the top first.
Yeah, so 1 3.
So 1 over 1, 1 over 3. And then
And there's 2, and there's 2 3.
2 over 1, 2 over 3. Yep. So if we're going to have a rational root, it's going to cross the x-axis at one of those numbers. And since they're asking us to find all real roots, it probably does. Okay, so we got to figure out which one of those numbers it is.
Do P and Q stand for something?
Just numerator and denominator, no specific word. Yeah. That's what the book uses.
Okay.
Okay, so 3x cubed minus 8x squared plus x plus 2. I'm going to do zoom 2, and I'm going to zoom in because I think I have to wait. Well, maybe I won't zoom in. I'll just make it picture bigger. Okay. Where does it look like it crosses the x-axis? And it has to be a number from this list.
Maybe 2/3.
Could be 2/3. I'd say that could be an option, or
-1/3.
yeah, it's one of those. It's not both of them, because I just think the other answers are going to be messy. So let's try positive 2/3. Let's do trace 2/3. 2/3 is a root. Let's try the negative 1/3. So hit trace, negative 1/3. Even though it looks like negative 1/3, it is not. Negative 1/3 is not a root. I can see why you would think it might be because it looks close. But 2/3 is the root. Yep.
In this instance, I know that there's only one of those options that works, but like, did you have multiple?
Yep. And then you just pick one.
Okay.
Doesn't matter which one you pick.
Alright.
So 2/3. And then on the outside, 3, -8, 1, 2. We already know what the remainder is going to be because we checked it. What's the remainder going to be?
0.
Remainder is going to be 0. So bring down the 3. What's 2/3 times 3?
2.
2. And then add that up, you get -6. What's 2/3 of -6? -4. Add that up, you get -3. What's 2/3 times -3?
-2.
-2
Comes out to 0.
comes out to 0. So we just proved 2/3 is a root. 2/3. And what do we have to solve now to get the other two? What's left? The quotient. So this is A, that's B, and that's C. It's not going to factor. It's going to have to be quadratic formula. So 6 plus or minus negative b plus or minus the square root of, what's b squared?
36.
Minus 4, 3, -3, 4ac. Yep. All over
2a, 6.
6.
36 minus 12 times -3, so 36. So 36 plus 30. 12.
36 plus
36.
Over 6. And then, this is why I was kind of hesitating, because you can really just write it like this. It's just 2 square roots of 36.
Yeah.
Divided by 6.
Hold up.
Square root.
6.
square root of 2 times the square root of 36?
Or it'd just be 2 times the square root of 36.
Square root of 2 times square root of 36.
Oh.
Wait, could you write 6 plus minus 6?
Oh, yeah, like-
And then what's the square root of 36? So we get 6 plus or minus
Yeah,
6 root 2 over 6.
yeah, that's what I was saying.
And then what happens there? 6's all cancel out. And you end up with 1 plus or minus square root of 2. Those are the other two roots. So the calculator cannot give you those other roots. It's going to give you a decimal, and most likely I'm going to ask for the exact answer. So you have to use quadratic formula to get it.
How did they get one?
How do we get 1?
Yeah.
6 goes into 6 one time. So I just canceled all my 6's and made them 1's.
Cancel both of them.
Yeah. Yep, you have to cancel it from here, here, and then. All 3 spots. Okay, if you don't simplify your quadratic answer as much as possible, it's not the end of the world, but you should.
I just thought you can simplify the outside 6 plus or minus. It's not.
So if you have like 6 plus 18 over 6, you can do this. That's okay to do. Okay, so the homework is on page 183, and that'll be up on YouTube in 2 minutes.